Welcome to the exercises for DGD 5. These will be on naive set theory from chapter 5. The first of which asks us to decide if pairs of sets are equal, to prove if they are equal, or to disprove that they are not equal. The first two sets are these here. All the multiples of 3, where x is a natural number which is greater than 7, and the set of all x, where x is a natural number. So these are not equal. And our proof, we have to show that one of these contains an element that is not contained in the other. We will do that as follows. Note that 1 is natural, so 1 is in this set. However, 1 is not in the other set. Also note that if x is natural and x is greater than 7, then 3x is greater than 21, which is strictly greater than 1. And in particular, this means that 3x is not equal to 1. So, if B is any element of the first set, this means, by this above discussion, that B is not equal to 1. So 1 is not an element of this set. Therefore, this set contains an element which is not contained in this set, which means that these sets are not equal. Part 2 gives us these sets, the set of all natural numbers plus 7, and the set of all natural numbers which are strictly greater than 7. These are equal. And to prove that they are equal, we will simply show that the first is contained in the second, and that the second is contained in the first. So let A be any element of the first set. Since it's an element that satisfies these conditions, this means that there exists a natural number such that A is equal to x plus 7. This means that A is natural by closure, and that since x being natural means x is greater than or equal to 1, this means that x plus 7 is greater than or equal to 8, which is strictly greater than 7. Now x plus 7 is A, so A is strictly greater than 7. Now since A is natural and A is strictly greater than 7, it satisfies the conditions of the second set. So A is in the second set. And so since a generic element of the first is also an element of the second, it means that the first set is a subset of the second. Now going in the other direction, if we let B be a generic element of the second set, this means that there exists a natural number such that x is greater than 7 and B is equal to x. So B is natural and it's greater than 7. This means, I'll just write that out, that B is natural and B is greater than 7, and B being greater than 7 means that B minus 7 is natural. Then B is equal to B minus 7 plus 7. So since B is a natural number plus 7, that means it's an element of the first set. So a generic element of the second set is also an element of the first. This means that we have a subset inclusion the opposite way as well. And since we have this subset inclusion and the opposite subset inclusion, this means that these sets are equal. Our third pair of sets is one of the sets that occurred in part 1, all the multiples of 3 where x is natural and greater than 7. And our second set is numbers of the form 3x plus 21, where x can simply be natural. These are equal. And so the proof will be the same as in 2. We'll show that these are subsets of each other. So let's take a generic element of the first set. This means that there exists an x, which is natural, greater than 7, and a is equal to 3x. Since x is greater than 7, this means that x minus 7 is natural. And then, if we look at a, this is 3x minus 21 plus 21, which can be written as 3 times x minus 7 plus 21. X minus 7 is natural. A is of the form 3 times a natural plus 21, which means it's in the second set. And this means that the first set is a subset of the second. For the reverse inclusion, we consider a generic element of the second set. This means that there exists a natural number x such that b is 3x plus 21. This we can write as 3 times x plus 7. And since x is greater than or equal to 1 because it's natural, x plus 7 is greater than or equal to 8, which is strictly greater than 7. So b is 3 times a natural number, which is strictly larger than 7. This means that b is in this set, our first set. So we get an inclusion the other way. The second set is contained in the first. And since we have both these inclusions, these sets are equal. Exercise 5.1.3 is similar. We have two sets, and we're asked if these are equal. The first set is S, and it's the set of all m, such that m is natural. So this is just the set of all natural numbers, so we can make a note that this is just n. And T sub m is the set that contains one element for a specified m. So for example, T sub 1 is the set that contains 1, T sub 2 is the set that contains 2, and that's it, depending on what the choice of m is. So here we can see that this has infinitely many elements, and these each have one element, so these are not equal. So not equal. Proof. Let m be specified. then since M is natural, M plus 1 is natural, and since it's natural, it's contained in S. However, M plus 1 is not an element of the set that contains M, which is T sub M. So we have an element of S, which is not an element of T sub M. So this means that S is not equal to Tm. Part 2 gives us the sets U and V sub M. The set U is all the products M times Y, where Y can be any integer, M can be any natural number, but M times Y must be greater than 0. And V sub M is also products M times Y, where Y can range over the integers, M times Y has to be greater than 0, but they're all with respect to a specified natural number M. First, I think it's easier to understand exactly what these sets are. This M here is relating to this specified M, whereas the M inside the notation for U is just a variable that can be any natural number. So we can rewrite U using any variable we want. Let's use X. And so now we see that these M are not connected. U is just this set of all products, whereas Vm actually depends on the specified M. We can further simplify U, so note, if A is a natural number, then A is equal to A times 1, where 1 is an integer, A is natural, and A times 1 is greater than 0 because A is natural. So A satisfies the conditions to be in U. And then also, if B is in U, then it satisfies the conditions to be in U. So there exists X, which is natural, Y, which is an integer, such that B is equal to XY, and XY is greater than 0. But if B is strictly greater than 0, this means that B is natural. So what do we have? If A is natural, then it's in U. This means that the natural numbers are a subset of U. And if B is in U, then it's in N, which means that U is a subset of the natural numbers. Having both of these inclusions, we see that U is just the natural numbers, written in a complicated way. Now let's look at Vm. Let's first consider V sub 1. We're fixing M to be 1. This means that V sub 1 is 1 times Y, where Y is an integer, and 1 times Y is greater than 0. If 1 times Y is greater than 0, then 1 times Y is natural. And if you have a natural number, it can be written as 1 times itself. So by a similar argument as here, this is equal to the natural numbers. Now, if the chosen M is strictly greater than 1, then V sub M is defined like this, My, such that Y is an integer, and My is strictly greater than 0. But now 1 will not be in this set. For instance, if M is 3, this will contain 3, 6, 9, just the multiples of M. If M is 5, this will have 5, 10, 15, etc. And it will not contain 1. So we can say, note, if Y is an integer and Y is less than or equal to 0, since M is natural, this means that My is less than or equal to 0, which means that My is not in Vm. So what this means by contrapositive is that if My is in Vm, then Y is strictly larger than 0, which is the same as saying Y is natural. If B is an element of Vm, then there exists y, which is strictly greater than 0, which is the same as greater than or equal to 1, such that b is equal to my. This is greater than or equal to m times 1, which is m. But if m is strictly larger than 1, this means that b is not equal to 1. So this means that 1 is not an element of Vm. So in this case, u is not equal to Vm. So in conclusion, therefore, if m is not equal to 1, then u is not equal to Vm, and u is equal to V1. Part 3 asks about the set Vm again, and about the set Wm, which is the products my, where y is any integer, but now only y has to be strictly greater than 0. Both of these rely on a specified m, and we're asked if these are equal. These are equal. As a proof, we will show that they are subsets of one another. So let A be an element of Vm. This means that there exists a y, which is an integer, such that A is equal to my, and this is greater than 0. Now, since m is natural and my is natural, because it's greater than 0, this implies that y is natural, which means that y is greater than 0. So A is equal to m times y, where y is an integer greater than 0. This means that A is in Wm. Therefore, since A was a generic element of Vm, and it must be in Wm, Vm is a subset of Wm. And for the other inclusion, if we let B be an arbitrary element of Wm, this means there exists an integer y is greater than 0, such that B is equal to m times y. But then since, again, m is natural and y is greater than 0, this means that my is greater than 0. So B is equal to my, where y is an integer and my is greater than 0. This means that B is in Vm, which means since an element of Wm must be an element of Vm, we have this inclusion. And with both these inclusions, we have that these are equal. (5.2.1) Part 1 gives us 3 sets, A, B, and E. And we're asked if it's true or false that A intersect E is equal to B, and to justify our answer with a proof. So A is all the natural multiples of 3, B are the multiples of 3 shifted by 21, and E are just all the natural numbers. So since A is already a subset of the natural numbers, intersecting with E doesn't do anything. So really we're just asking if A is equal to B, and these are not equal. Everything in B is larger than 21 because 21 is being added, whereas A contains elements such as 3 and 6 and 9. So no, these are not equal. To prove this, we have to demonstrate that there is an element in one of the sets which is not in the other. And we will do that as follows. First, let B, little b be an element of B. This means that there exists a natural number x such that B is equal to 3x plus 21. However, since x is greater than or equal to 1, this means that 3x is greater than or equal to 3, which means that 3x plus 21 is greater than or equal to 24, which is strictly larger than 3. This means, since B is of this form, it must be strictly larger than 3, so B is not equal to 3. Since B was a generic element, this means that 3 is not an element of the set B. However, since 1 is a natural number, this means that 3, which is 3 times 1, is in A. And since 3 is natural, this means that 3 is in E, which is just the set of all natural numbers. Since 3 is in A and it's in E, this means it's in the intersection. So we have an element in the intersection, well, we have an element in our one set, A intersect E, which is not in our other set, B. Therefore, A intersect E is not equal to B. Part 2 gives us the sets A and B again, now with set C, which is all the elements x plus 7 where x is natural, and we're asked if A intersect C is equal to B. So C can be thought of as all the natural numbers which are strictly greater than 7. So A intersect C will be the multiples of 3 which are strictly greater than 7. And we're asked if this is the same as B. However, as we saw last time, the elements of B are all strictly greater than 21, and there are multiples of 3 which are greater than 7 but less than 21. For instance, 15. Therefore, there will be an element in A intersect C which is not in B, and so these are not equal. Proof. As shown previously, for an element in B, we know that B is greater than or equal to 24. Note, since 8 is natural, this means that 8 plus 7, which is 15, is an element of C. And since 5 is natural, this means that 3 times 5, which is also 15, is an element of A. This means that 15 is in A intersect C, but since 15 is strictly less than 24, 15 is not an element of B. So since A intersect C contains an element which B does not, these sets are not equal. Part 3 continues with the set A, brings back the set E, which is the set of all natural numbers, and works with F, which is the set of 3x minus 21, where x is natural. And we're asked if E intersect F is equal to A, and in this case they are equal. So the proof, to show that two sets are equal, we will show that they are contained in one another. So let's let A be an arbitrary element of the set A. This means that there exists a natural number x such that A is equal to 3 times x. Now we would like to write it in the form 3 times a natural number minus 21. And what we can do is we can write that A is 3 times x plus 21 minus 21, which is equal to 3 times x plus 7 minus 21, where x plus 7 is natural by closure of addition. So A is 3 times a natural number minus 21. This means that A is in F. And since A is natural by closure under multiplication, because it's just 3 times a natural number, this means that A is in E. Since it's in F and it's in E, this means that A is an element of E intersect F, and so the set A is a subset of E intersect F. If we now let B be an arbitrary element of E intersect F, this means that B is an element of E, and that B is an element of F. So we can unpack what each of these means. This means that B is natural, because it belongs to E, which only contains natural numbers, and that there exists a natural number x such that B is equal to 3x minus 21. 3x minus 21 we can write as 3 times x minus 7. And now since we know that B is natural and that 3 is natural, x minus 7 must also be natural. So x minus 7 is natural, and therefore we have that the element B is 3 times a natural number, which is sufficient to belong to A. So this means that B is in A. So our arbitrary element of E intersect F belongs to A. This means that E intersect F is a subset of A. And now that we have both subset inclusions, this means that E intersect F is equal to A. 5.2.2 asks us to consider 3 generic sets, A, B, and C, and to decide if the following by implications are always true, or if they can be false, and if they can be false, to provide a counterexample. So part 1 says that if C is a subset of A and it's a subset of B, is this equivalent to C being a subset of the union, A union B? And this is not equivalent. So to demonstrate, we do have, so claim, we do have the forward implication. C is a subset of A and C is a subset of B does imply that C is a subset of A union B. We can prove this claim. So let A, B, and C be sets, and assume C is a subset of A and C is a subset of B. Since C is a subset of A, we know that if we let X be an element of C, this means that X is an element of A. This means that X is an element of A or X is an element of B, because you can tack on any proposition with an or. And if X is in A or it's in B, this means that X is in the union. This chain of equalities means that all the elements of C are elements of A union B, and therefore C is a subset of A union B. So we've proved our claim. However, the implication in the opposite direction does not hold. The converse is false. So our other claim is that C is a subset of A union B implies C is a subset of A and C is a subset of B is false. To show that this is false, we need to provide a counterexample of sets A, B, and C, where C is a subset of the union, but it is not a subset of either or. So, consider the counterexample. This is our proof. Consider the counterexample. A is equal to the set that only contains 1. B is equal to the set that only contains 2. And C is the set 1, 2. Well, then C is equal to A union B. So C is a subset of A union B because every set is a subset of itself. But C is not a subset of A, since 2 is in C and 2 is not in A. So the conclusion that C is a subset of A and that C is a subset of B is false. This counterexample satisfies the assumption but does not satisfy the conclusion, therefore showing that the overall implication is false. Part 2 gives us a very similar looking by implication. However, the and has been replaced with an or. So now we're asked if C is a subset of A or if it's a subset of B. Is this equivalent to being a subset of the union? And this is not equivalent. The forward implication still holds. So claim C is a subset of A or C is a subset of B implies C is a subset of A union B. This is true. We can prove this. So let X be an element of C. Now what we have is that C is a subset of A or C is a subset of B. C being a subset of A would mean that X is in A. This is connected by the or to C being a subset of B, which would mean X is in B. Now if X is in A or it's in B, this means that X is in the union. So all the elements of C are in A union B. This means that C is a subset of A union B. However, the converse does not hold. So claim the implication that C is a subset of A union B implies that C is a subset of A or C is a subset of B is false. And we can use the same counterexample. In the previous counterexample, all we had to show was that C was not a subset of A, since we were disproving an AND statement. Now we're going to disprove an OR statement, but it wasn't a subset of either, so it still works. So proof, consider the counterexample. A is equal to 1, with a set containing 1. B is the set containing 2. And C is the set 1, 2. Then C is a subset of A union B, because this is just equal to C. But C is not a subset of A, and C is not a subset of B, which means that the conclusion fails while the premise is satisfied. Therefore, this overall implication is false. Part 3 asks if it's equivalent whether C being a subset of A and a subset of B is equivalent to C being a subset of the intersection, A intersect B. Now this is true. This is equivalent. So since it's true, we can prove it. So let A, B, and C be sets. First, we'll prove the forward direction. So we assume C is a subset of A and that C is a subset of B. So now, let X be an element of C. This means that since C is a subset of A, that X is in A, and also since C is a subset of B, that X is in B. Now, since X is in A and B, this means that X is in the intersection. So all the elements of C are in the intersection. This means that C is a subset. That is the forward direction. Now if we look at the reverse direction, we now assume that C is a subset of A intersect B. We're going to let X be an element of C. Now, since it's an element of C and it's a subset of the intersection, this means that X is in A intersect B. But this means X is in A and X is in B by definition. So we have two overall implications here. We have X in C implies X is in A. Therefore, C is a subset of A. And we have that X is in C implies X is in B. And therefore, C is a subset of B. So C is a subset of A, and C is a subset of B, which is the left-hand side where we were trying to get to, which completes the proof. The last part, part 4, asks if C being a subset of A or C being a subset of B is equivalent to C being a subset of the intersection, A intersect B. And this is not equivalent, because the forward implication is what fails. So our claim is that C being a subset of A or C being a subset of B, implying that C is a subset of the intersection, is false. So proof, consider the counterexample. A is going to be the set 1, 2. B is going to be the set 2. And C is going to be the set 1. So then, C is a subset of A, since the only element it contains is also contained in A. And therefore, C is a subset of A, or C is a subset of B. Since the first part is true, the entire OR statement is true. However, C is just equal to the set 1, and it is not a subset of the set which only contains 2, which is A intersect B. So, the premise is satisfied while the conclusion fails, so this implication is false. However, the converse now does hold. So the fact that C is a subset of the intersection does imply that C is a subset of A, or that C is a subset of B. And for our proof, we will simply use case 3 above. So by 3 above, we know it is true that C being a subset of A intersect B implies that C is a subset of A and C is a subset of B. This means that these are both true, which means that the OR statement is true. Therefore, we have the implication C being a subset of the intersection implies that it's a subset of one or the other. 5.2.3 says, suppose we have a set Y, which is a subset of X. We want to prove that the double complement of Y is just back to Y. So proof. So to show that two sets are equal, we could show that one set is contained in the other. However, we can also show that it is equivalent for an element to belong to this set and that element to belong to this set. So we'll have a chain of equivalence here. So let X be an element of the double complement. Well, this is, by definition, X not being an element of the complement. This is equivalent to just writing the negation this way, not X is in the complement. But now X belonging to Y complement is equivalent to X not belonging to Y. And if we negate the fact that X does not belong to Y, we just get that X belongs to Y. So belonging to the double complement is equivalent to belonging to Y. Therefore, the double complement is equal to Y. 5.2.5 again wants us to consider three generic sets A, B, and C, and we are to prove or provide a counterexample for some statements. The first statement is whether the set A remove the set B union C is always equal to A remove B union A remove C. Now this is false. These are not always equal. So consider the counterexample. we're going to let A be the set 1, 2, B be the set 1, and C be the set 2. Then we can just compute each side and see that they are not equal. So A remove B union C. A is the set 1, 2. We are removing B union C is also the set 1, 2. So since we're removing all elements from the set 1, 2, this is just the empty set. However, on the right-hand side, A remove B is the set 1, 2, remove the set 1. And A remove C is the set 1, 2, remove the set 2. 1, 2, remove 1 is just 2. And 1, 2, remove 2 is just 1. So this union is 1, 2 again, which is A. So the left-hand side is empty. The right-hand side is A, which is non-empty. So these are not equal for this counterexample. Part 2, the last part, asks if this equation is always equal for all sets A, B, and C. And this one does hold. So we can prove it. So to prove two sets are equal, we can show that they are subsets of one another. So to show the first inclusion, let X be an element of A intersect B minus C. Since it's an intersection, this means X is in A and X is in B without C. This, X being in B without C, means X is in B and X is not in C. Now, since X is in A and B, this means X is in A intersect B. Then, since X is not in C, and A intersect C is a subset of C, it must not be in A intersect C either. So we have that X is in A intersect B, and it is not in A intersect C. This means that X is in A intersect B without A intersect C. X was a generic element of the left-hand side, so this means that A intersect B minus C is a subset of the right-hand side. A intersect B minus A intersect C. To go the other way, let's let Y be a generic element of A intersect B minus A intersect C. By the definition of set difference, this means that Y is an element of A intersect B and Y is not an element of A intersect C. This we can unpack as follows. This means Y is in A and Y is in B. This we're going to first write as the negation of Y being in A intersect C. We can expand this into Y being in A and Y being in C. Then we can distribute this negation to get Y is not in A or Y is not in C. Now, I'm going to bring this Y is in B, we'll just leave this on the front, and I'm going to distribute this Y being in A over this OR. So we get that Y is in A and Y is not in A, or Y is in A and Y is not in C. However, Y being in A and Y being not in A, this is always false, which means that the other part of our OR statement must be true. So we get that Y is in B and all we're left with is y is in A and y is not in C. These we can rewrite as y being in A, and since it's in B and not C, y is in B without C. And then since it's in both of these, y is in the intersection. Therefore, since we started with an element of A intersect B without A intersect C, it must be a subset of the set we ended up in, which is A intersect B minus C. Then we have both inclusions, so these sets are equal.